Hi, this is Aditya, and along with my project partner Kaishavi, we'll be demonstrating Laboratory 9 assignment of the course EE542, which talks about Spark and its comparison with Hadoop and MPI. So, first, we'll familiarize with what Spark is and how we are using PySpark API to basically do a machine learning task. First, we'll practice this in local mode, and then we'll extend this in the AWS Elastic MapReduce, right? And then after we do that, we'll basically come to the main goal, that is to compare what we did in the previous two labs, that is word count and character count, and use it for different working nodes, right? And then compare how PySpark performs and how Hadoop and MPI perform with varying number of nodes, and then draw a comparison and a conclusion. So that's the agenda for this video demonstration. So Spark is based on a computational engine. It takes care of scheduling, distributing, and monitoring application, and it's basically used in big data technologies so that it can basically assign tasks to one machine. One machine performs one task, and while the others contribute to the final output through a different task. So the main advantage of Spark is to build an architecture that encompasses data streaming management, seamlessly data queries, machine learning prediction, and real-time access to various analysis. So let's get started. So the first part of this lab is to basically practice using Spark in local mode on a single node machine. So the machine that I've created is an EC2 instance using the Amazon Linux 2 AMI. So I've selected the c5.large instance type, and if you need to install a Docker using basically our yum, and then after you install Docker, you need to get the Docker name. In my case, it's Frosty Ganguly, and with that, I've already installed. I can already see that my Jupyter notebook is running on this URL, right? So this is my Jupyter running on my Amazon instance. So the purpose of this particular section of the lab is to apply a machine learning algorithm and then basically forward this. Basically extend it to the cluster mode. So right now I'm running it on a single node machine, right? So these are the files that I have: xtrain, ytrain, ytest, and xtest. So let me explain about the files. So this is the dataset that we have. This dataset is basically a smartphone based recognition of human activities and postural transitions dataset. So based on the sensors on an Android phone, using its accelerometer and gyrometer on a time and frequency domain, we basically the dataset basically gives us the values of what the person is actually doing, and it's been experimented on around 30 volunteers, right? So we have this. So this dataset is basically divided into two parts. So first is initial sensor data, which has the raw data and the labels for that particular data, and then the records of activity windows, which is each composed of a 561 feature vector, right? So these 561 features will be used in training our model basically, and we have this associated activity label. So what are the activity labels? These are the activity labels. So one is basically walking, 2 is walking upstairs, 3 is walking downstairs, and so on, right? So I already uploaded the necessary files, that is features.txt. In the test data, I have my xtest. So my xtest corresponds to the 561 feature, and the ytest is basically the activity label. Same for train. Xtrain is basically features, and ytrain is basically activity, right? So these are the only required data that I need to run my machine learning model, right? So my notebook is already running. So using this test Python script, I was able to basically form a CSV file using these test files and club it. So my test underscore data has both my 561 features as well as my label, activity label, and same for train, right? So I'll be attaching these files in my submission, but I'll be explaining my PySpark ML program just for the demonstration purposes. So first we create the Spark context object, and then I've already given my file path as train underscore data.csv. So in this way I can form my data frame underscore train, and you can see that this is the schema. So these are all the headers, these are all the 561 features basically, and I can see that at the end it's the label is there, which is an integer, right? So this is just to show that this is the first row. So the df underscore train.show gives you the first row. So these are the headers and the corresponding values, right? So after I do that, I basically want to vectorize all my features. So essentially I should have only a label column and a features column which has all the 561 features, right? So this step performs that. So this is called building. So I'm building a pipelining just so that I can structure my code in a better way, and then I transform my data frame in the way that I want to, right? So that's how I'm doing this. So I'm feature calls is the basically I'm letting know that the features, what of feature headers I want to be clubbed as features using vector assembler, right? And then I'm using pipelining to basically form that transformation. So I will do that transformation. I get my train underscore data after I do RDD map and get the label and features from the model, which is my transformed data frame. So I get train underscore data, which I create a data frame using the input data, and then I mark them as label and features. And then as you can see, I'm just showing the first two rows. So you can see that label contains only a singular value, which corresponds to the activity, and features is basically on all the 561 features in a vectorized format, right? So you can see that running this command, I could know that what label corresponds to how many basically occurrences in the data set. So for example, one is walking, right? So there are 1 2 to 6 data sets corresponding to walking, right? So we have this trained data set ready, and what I do is I'm using a random forest classifier. Why? Because we have multiple classes, right? So we cannot use binary classification, and random forest is basically a more uh, scaled version of decision tree. So basically random forest is basically multiple decision trees, and each decision tree has a depth of 7, and I'm keeping my number of decision trees as 15. So that's what the arguments mean. I specify what my label column is, and I specify what my features column is. So that's how I get my RF, and then I fit that model on my data set, and I calculate the time that it takes from start to end. So as you can see that the time that it took me is around 43.4 seconds just to train the model. Then essentially I've already trained my model is ready. Now I need to test my model on the test data set, right? So for that I basically reproduce all the steps that I just explained in this particular script. It's everything is same, I'm just using the test data set now, right? And then I apply my model on the first I applied my model on my training data set, and as you can see that I'm getting a training accuracy of 95.57%, and then I do the same on the test data set, I get a 87.35%, right? So this is using the confusion matrix, and I'm just checking the accuracy by just checking whether my predicted value and the corresponding label is equal. If it's equal, then I'm going to count it divided by the total count. So that's simple fractions. So that's how I'm getting my training accuracy and test accuracy. And for test F1 score, I'm using a multi-class classification evaluator. So this evaluator basically has an attribute to basically directly get the F1 score, which is convenient for me. And as you can see, the test F1 score that I'm getting is 0.87, right? So let's just do a trial run. So I've already started my Spark context. I'll do my SQL context. It's ready. And then I'm forming my data frame train. And you can see I got all my headers. This will show me the first row basically, and then I'll do pipelining. just so that my model is more structured and my features get vectorized. Displaying the model take one, basically the first row. And now I'm using input underscore data just to get the RDD version of it, and I'm creating a data frame for label and features. So my training data is formed in the form of data frames, and as you can see, I'm able to display the first two rows, right? So I do this just to get the count of how many frequencies how many occurrences is there per label. It's gonna take some time, and once I have this, I'll then start training my model. So this is also again gonna take, as I mentioned before, it took me around 43 seconds. So this also should take about a minute, like within a minute. Yeah, so it took 44 seconds now, and I'm now first doing basically reciprocating the same steps for test data set, right? Now I'm gonna run the model on my training data set just to get my training accuracy, and let's see how much I get. So earlier it was 95, should be around 90, more than 90 I'm expecting. Yeah, again it's 95.944, and let's run this. So this is on test data set. I'm calculating my test accuracy, again 87.255, and finally I'm going to calculate the F1 score. That's around the same, right? So now I'm going to extend this towards, I'm going to extend this on the cluster. So now we will practice running a Spark job on a real cluster using AWS Elastic MapReduce, that is AWS EMR for short. Right. So before we do that, we need to basically load our files on the S3 bucket. So Amazon S3 is basically like a storage, and we could access the files from this bucket from our cluster, right? So Spark is a distributed computing framework, right? So it's not primarily designed to be used on a single node machine. And when we ran the Spark in local mode, it basically allocated the tasks, the machine learning tasks, to local threads instead of the worker nodes, right? So this is how Spark is actually designed to work, right? So there are a few changes that needs to be done from the previous Python notebook, which we incorporated using PySpark ML, right? So if you can see in the previous case, we imported PySpark. We don't need to do that because the kernel that we are running is PySpark in itself, so it's already loaded and the SC object is already created. So we first import the Spark session, and the session is done, right? So we have to make some configuration settings so that a cluster can access our files in the S3 bucket. So we need our access key and we need our secret access key for that. And when we run that, we go to basically, then now we are able to read the CSV files. So this is more or less the same as doing SQL context, but here we are not using SQL context, we are using Spark session, right? That's the only difference here. So basically it tells you the job progress as well, and it shows you the elapsed time as well, like how long it took for the Spark job. And when we print it, you can see that our headers, we get it as the required data type, right? So I was facing an error loading the features.txt using file open, and I was initially using this just to have a list of all the headers so that I could just use vector assembler and club all the columns, all the feature 561 feature columns as one features, right? So instead of, I was facing some error, so the short hack that I found is just creating the list. Just I output the feature columns on my local node Spark and then just print it here. I mean, just paste it here, and it worked. So it looks ugly, but this is the short fix that I found. And then basically use vector assembler, set the stages, and then use pipeline so that my code is structured. And after I do that, I'll basically create my data frame, which is train data, and I'll be displaying the first two rows. So it will have label and features, and the features is a vector of 561 entry points. Okay, so this is what we expect because it's the same, right? So we are getting the same thing, and just to see that the numbers are same, we're just basically counting how much is there per label. Again, this is also a Spark job, so it's working on the worker nodes, and you can see these are the counts, right? I'm using the same classifier, no changes made regarding this. So in the single node, I was getting around 43.4 seconds. So technically, it should be less than that because it's working on a separate node, right? So it took 25 seconds, which is a pretty good number compared to 43, right? So after I do that, I'll basically reproduce the same steps to have my test data frame, and then I'll apply my model on the test data to get the test accuracy. So it's 96. What did I get here? I was getting some 95. It varies according to the model, right? And calculating the test accuracy now. So all these things are same. I'm just running it. So the only changes that were different were the feature column string and the configuration settings so that our cluster can access the CSV files. So we're getting 82.234, which was better than before, right? And let's calculate the F1 score on the test data. So we're getting test F1 score as 0.88, right? So this is just a short demonstration of the step 2 that is being accustomed to working on an elastic MapReduce, right? So I'll just take some more time to just explain how I created the cluster. So in the cluster, let's reload this. Yeah. So you can see here that I used two nodes. It's a two-node cluster, and each instance is M5 .xlarge. It's a general purpose, and that's what it was recommended for us. And I'm using this on my VPC 10.0.06 VPC, 10.0.0.0/16 VPC, and the subnet that I'm using is same as I used in the previous lab. That's why it's named as lab 8 Hadoop, right? So so that means that the two nodes are in the same subnet. That's the point I'm trying to make. So this is how I created my cluster, and that's how EMR Spark is run on distributed frameworks. So the next steps is basically doing the same thing with word count and character count for the 1 GB data file on the Spark, Hadoop, and MPI, and then compare all the three. So the next thing that we have to do is to run our word count and the character count program on variable working nodes on Hadoop. So I'm starting with two worker nodes and one name node, and I've already done all the setup, and I've already copied the file system that we have to run it on. So the Gutenberg folder has the 1 GB text file, and on this text file I'll be running the WordCon program, right? So let's get started. So I'm using the more or less the same WordCon program. Few changes which are not really impactful. I'm gonna make some changes here and there. Yeah. So first I'm running the word count program using my this file system, which has two worker nodes and one name node. And as you can see, the process has begun, and it's gonna take some time. So I'm gonna pause my recording and resume once it's done. I'm just waiting for the mapping process to start. Yep, so the mapping process has begun, and I'll resume the recording once it's done. Yeah, so the job just finished and without errors. So let's see if there's a change on the directory. Yeah, you can see that the output directory is created with the output file, and we can also look at the GUI, cluster GUI, to make sure how long it took. So as you can see, we started at 14:07 and the finish time was 14:15, so it's roughly 8 minutes for the word count on the 1 GB file. Right, so to see what the output file is, I'll run this command and we'll get to know the minimum and the max. So you can see that I'm printing out the words that have a minimum frequency of 1, and the word with the max frequency is actually 9736298. Right? So what I'll do is now I'll delete the basically the output directory and run my character count program on the same. So user Ubuntu Gutenberg output. I'll just cross check if that's the same. Yeah, so user Ubuntu and then Gutenberg output. So I'm deleting that directory so that we could reuse. We could reuse it for the character count program. Right. So as you can see, I've already changed the MapReduce program, which has the character count program in it, and I'll basically run the same command to run my job. So you can see that it has started the job, Hadoop job, and it's gonna take some time. So yeah, the mapping process, I'm just waiting for the mapping process to start so that I can pause the recording and then resume once it's done. Yeah, so the mapping process has begun. So I'll pause the recording now and then resume once it's done. So you can see that the job has been finished and we didn't get any errors. Let's take the GUI. Yeah, so it started at 14:21 and it took 14:55, so roughly around 34 minutes. That's how long it took. Right, so we could also see the updated file system here. Right, this is where we have our the output file. So let's view our output file. Yeah, so this is our output file, right? So it'll show us that slash is the character with minimum frequency with 954, and E is the maximum frequency, right? And these are all ASCII characters greater than 33 and less than 122. That's what was required. So that's the only change from the previous lab. So now I'm going to extend this for 3 working nodes and basically do the same word count and character count program, and then again for the 4 working nodes. Yeah, so I've added one more working node, and I've already copied the directory that has the 1 GB file. Let me show you that. Yeah, so this has the 1 GB file, and I'll be performing the word count program first with 3 working nodes now. I'll also show the GUI. So the first task is just the example task, just to check whether all my Hadoop cluster is working. So I'll be running that now. I'm just looking for the command to run so that I don't have to write it. Yeah. So let's make some changes. So as you can see that the process has begun, and I'm just waiting for the mapping process to start. Yeah, so the mapping has begun, and I'll resume the recording once the job is done. So we can see that the job has been finished, and let's see how long it took. So for the word count, it took around 8 minutes, right? 1729 and 1737. So around 8 minutes it took for the completion. And let's see what the output is. For output, we'll just there. Okay, now I have to write it. HDFS minus cat. Let's check the file system as well. So if we reload it, you can see that there's a new output generated, and this particular file has the output. So it's part 5 times 0. So you can see the word with minimum frequency is being printed, and we're getting 9736298. This is the expected number of this is the maximum that has been printed, right? So now I'm gonna run the character count program, and let's see what that happens. Yeah, so I replaced the mapper and reducer programs with the character count program, and now I'm gonna delete the output file. So that's there. Minus R minus F. Gutenberg output. Oh no, there's the Ubuntu in between. Yeah. So when I do that, yeah, there's only the Gutenberg folder which has the 1 GB file. Now what I'm going to do is I'm going to run the same command for character count and see how long it takes. And yeah, so again this has begun the process, and I'm gonna pause the recording once it starts mapping and then resume once it's done. Yeah, so the mapping process has begun. I'll pause the recording and then continue once it's finished. So the job just finished, and let's see if the output directory is there. Yeah, we can see the output directory now and the elapsed time. Yeah, so you can see the start time is around 2022, the finish time is around 21:02, which is roughly 38 minutes, 39 minutes, around 40 minutes, right? So it took 40 minutes. And let's see the output of the file. Okay, let's view it. Yeah. So you can see that we are getting the expected result. Character of the max frequency is E, and minimum frequency is 954, that is slash. Right. So this is the performance with having 3 worker nodes. Now we're going to try it on 4 worker nodes and run our same word count and character count program and then compare the results. So now you can see I added one more additional data node. Now I have 4 data nodes that is working nodes and 1 master node, right? I've already included the mapper and reducer programs for word count, and let's see the GUI. So this is the previous ones. Yeah, so this is the new GUI, and this is just an example just to check whether my cluster is working. And yeah, so this is the Gutenberg folder that has the 1 GB text file, right? So let's run our Hadoop program. So first I'm running the word count program, and as you can see the job has begun. And again I'm gonna pause the recording, and then once it gets finished and I'll resume the recording. So I'm just waiting for the mapping process to start and then I'll pause it. Yeah, so the mapping process has begun, and I'll pause my recording here, and then once it finishes I'll resume the recording. You can see that the job has finished, and just to confirm that it is indeed finished, we'll see whether the directory is created, and it is. So you can see that the output file is generated, right? Let's check the GUI for the elapsed time. So it started at 21:29 and it took around 7 minutes. Yeah, exactly 7 minutes. It's crazy. Yeah, so exactly 7 minutes here. So now what I'm gonna do is I'm gonna check the output file for that. So we know that the output file is in the Gutenberg output directory, and the file name is part45. Yeah. So you can see this is the output that we are getting, and the output is as expected, right? So now I'm gonna change all my mapper and reducer programs and run the character count program, and again repeat the same process. Yeah, so I've already replaced the mapper and the reducer file with the character count programs, and I'm gonna run the job now. Oh, I think I forgot to do one thing. I forgot to delete the existing output file. Right, so I have to do that. -r-f /user/ubuntu /gutenberg output. This will delete the whole output directory, and then I can run my output command. It's just to confirm that the directory is no more. We'll reload, and yeah, we just have the directory which has the 1 GB file, and let's run it. Right. So again, it's same process. I'll pause the recording here, and once it's done, I'll resume the recording. So I'm just waiting for the mapping process to start, and then I'll pause the recording. Yeah. So I'll pause my recording here, and then I'll resume once it's done. So we can see that the job just finished, and just to confirm that it has, we'll reload it, and you can see that it succeeded. So the elapsed time that it took was around 21:52 to 22:26, right? So this is around 30 minutes, less than 30 minutes actually, right? So that's how long it took, and we can see the output directory has also been created. Now we'll print out what we have in the output directory. Yeah, so this is the expected output. The character with max frequency is Z, and the character with min frequency is slash. So we can basically conclude that it worked perfectly. Right, so this is a character count program with 4 working nodes or data nodes and 1 name node. And this concludes the demonstration for this particular part of the assignment.
So now we'll compare Hadoop and Spark with MPI, and so we will execute word count and character count program on MPI using 2 nodes. Here we can see in host file that we have 2 nodes, so we have total 4 processors, 2 processors per node. Now let's execute first word count for 4 processors. It means 2 nodes. So we can see that process 0 is sending the chunks of file to count the words in it to other processors. And now we are waiting for the hash map to create in the processors. It will take a while. So here we can see that process 0 has received the hash map. So it is printing the minimum word count, the word which is used single in the 1 GB file. So we can see the maximum word count is the, and the time taken is 124 seconds. Now let's execute the character count code for 2 nodes. Same as a word count, Now we will wait for the hash map to create in 4 processors. It will take some time. So here we can see that we are getting hash map from various processes. So we can see that the maximum character count is E and minimum is slash, and so the time taken is 105 seconds. So now we will execute this code for 3 nodes. As you can see that now we have 3 nodes, so 6 processors. Let's execute the code of word count first for 6 processors, means 3 nodes. Now we are waiting for the hash map to create. So we are receiving the hash map from the processor. It is printing minimum word count. We can see that it is only taking 91 seconds to run this code, which is lesser than the 2 nodes. In 2 nodes, we had 124 seconds, and for 3 nodes, we are having 91 seconds. Now let's execute the character count for 6 processors, means 3 nodes. So we are receiving created hash maps from other processes, and we can see that it is done in 69 around 70 seconds, whereas with two nodes it was around 105 seconds. So we have saved a lot of time by increasing the node. So now let's do it for 4 nodes. As we can see, we have 4 nodes, means total 8 processors in our cluster. So now let's execute first word count for 8 processors. File is divided between processors. Now we are waiting for the hash map to create and send to the root processor. It will take some time. So we can see we are getting hash map from the processors. Hash map is ready, and now it is printing the minimum word count. Single word used in the file. We can see that it is taking 76 seconds only, which is much lesser than three nodes. So now we'll execute the character count for 4 nodes, means 8 processors. File is divided between processors. We are waiting for the hash maps to create. It is being created. Now we can see that it is taking only 52 seconds for character count of 1 GB file in MPI for 4 nodes. So it is much lesser than 3 nodes. Now let's run the word count and character count program on PySpark. So this is a cluster of 2 nodes on AWS. This is a Jupyter notebook. So this is needed to access the file from S3 bucket of AWS. Now let's first understand the code of character count. So here we have read the file, 1 GB of file, and then we are splitting the words from that file using flatmap lambda function, and then we are mapping it to a tuple of a word and its one count, and then we are splitting the words into characters using flatmap. We are splitting up the tuple into and taking out the word of the tuple, and then we are mapping it to the character, and then at last we are reducing it by the key. So at final in output we will get the counts of character and we are printing it. We are using time it function to note the time. Let's run the code. So as you can see that it is in progress. This is the elapsed time. We can see the time here too. Now let's understand the word count code until it gets done. So in word count, it is we are reading the text file and mapping using flat map lambda function. We are splitting it into the words, and then at last we are using reduce by key to count the words in the file. So this way we can calculate the word count of the file using PySpark. Here the words, pairs and text file, these all are RDD. So it will take time. So we can say it's progress here. So what is done? We can see the character printed here. It is taking around 380 seconds. Max count character, main count character. Now let's run this code, the word count code. So as we talked about the RDD here, RDD is a fundamental data structure of the Spark resilient distributed datasets, and it is immutable distributed collection of objects. So this is only read only. That's why every time it creates new RDD when we perform transformation and action. Here we can see the progress. about to complete. So here we can see the output of word count for 2 nodes. So it is taking 132 seconds to calculate the word count. Maximum word count is the Now let's run the word count and character count code on 3 nodes on Spark. So this is AWS notebook, Jupyter notebook. We are using Elastic MapReduce on AWS. Okay. And use Spark session available as Spark. Let's run this word count program. So this is 3 nodes. So it will be faster than the 2 nodes. We can see the progress here. So reduced by key task is completed in around 64 seconds. Now we can see here the words are printed. So we can see that it took around 76 seconds. Maximum word count is the Now let's execute the character count code. So it might take a while. So we can say that it is completed around in 193 seconds, 194 seconds. So here is the output for character and word count for 3 nodes. So now let's run word count and character count program for 4 nodes on Spark. Now let's run the word count program. So here we can see that we have got output of word count program for 4 nodes. So it is taking 59 seconds. Which is lesser than with number of nodes 3. Now let's just execute character count program. It will also take some while. So here we can see the character count. It is taking 134 seconds, which is lesser than nodes with number of nodes of 3. So this is for output for 4 nodes in Spark. We can see as we increase the number of nodes, we are getting output in much lesser time. and also it is much lesser than Hadoop, as Spark uses RDD, resilient distributed data sets, which is in memory implementation. So it cache the intermediate data when we use iterative program, but it is more than MPI, because we in MPI we have control on lower level system. So MPI is faster than Spark and Hadoop both. So we have got the best results in MPI, but Spark is better than Hadoop and it is much more easier to use than MPI. So here we can see the output of character count for 4 nodes on Spark. It is taking 153 seconds to execute this program. So till now we have seen word count and character count program for PySpark, Hadoop and MPI, and we have observed that the MPI had taken the least time among them, and the PySpark is much more faster than Hadoop. So here we will conclude that as we know that Spark is widely used in the big data industry since it can achieve better performance in response time, because in the in-memory access over the distributed machines of cluster will proceed during the entire iterative process. So Spark provides a data structure called resilient distributed data sets, through which it caches reused data and intermediate results in memory across machines of cluster during the whole iterative process. This is very efficient for improving the performance of those iterative jobs that have low latency requirements. So from our experiment, we observed that the MPI takes least time to execute the program, whereas Hadoop takes the maximum time among them. So Spark takes more time than MPI, but lesser time than Hadoop. So Spark is also user-friendly and easy to learn, with giving better performance than Hadoop. So we have successfully completed our Lab 9 EE542. Thank you.